Okay, this lecture is about differentiable functions. We're going to do some definitions. Before we do our definitions, we're going to motivate them. And start out, the motivation is about getting a good error function for, or a good error estimate for our function. And so let's start out assuming that we can have that we have a function that we know is a good function. And here, just for the sake of it, let's say that we have a function which is expressed as an infinite series. In this case, okay, if for values of x that are close to a, the squared term and the terms beyond that will be very small, and so f is approximated by a naught plus a1 times x minus a. So it's approximated by a line. Okay, the error is therefore the difference between this line estimation and all of the functions, all of the terms that are degree 2 and higher. Okay, so note if there is an interval for which the power series converges to a continuous function, that u of x has the property that the lim as x approaches a of u of x over x minus a is equal to, okay, the limit where we've divided 1 power of x minus a out of our u, and that will go to 0. Okay, and so this is another way of saying our error function is very small. Okay, so given this page, let's go ahead and define a differentiable function. Okay, suppose that a is a subset of the real numbers and that little a is an element of capital A, such that a minus delta, a plus delta is contained in a for some delta greater than 0. Let f from a to be a function from a to r. We say that the function f is differentiable at a if there is a number L and a function u of x such that f of x is equal to f of a plus L times x minus a plus u of x. Okay, so in other words, our function f is linear with a nice error function. Okay, so this u of x over x minus a, its limit will be equal to 0 as x approaches a. We say that L is the derivative of f at the point A, and we will denote it by f prime of A. All right. Likely as not, you've never seen this definition before. So let's go and let's connect it with the definition that you did see in Calc 1. Let f from a to r be a function. Then f is differentiable at a if and only if the limit as x approaches a of the fraction f of x minus f of a over x minus a is equal to L for some real number a. In this case, L is equal to f prime of a. So this is an if and only if. Okay. We take two directions on it. Okay. First, we assume that f is differentiable at a. Since f is differentiable at a, f of x is equal to f of a plus f prime of a times x minus a plus u of x, where, okay, the limit as x approaches a of u of x over x minus a is equal to 0. Okay, so what we can do now is to subtract f of a from both sides of this equation and then divide both sides by x minus a so as to get the f of x minus f of a over x minus a is equal to f prime of a plus u of x over x minus a. Therefore, the limit of our difference quotient, as you called it in Calc 1, is equal to f prime of a. So there you go. Now let's take it the other direction. Suppose that we do have the limit as x approaches a of f of x minus f of a over x minus a equal to L for some real number L. Define u of x to be f of x minus f of a minus L times x minus a. So we're just taking here the difference between f of x and the line f of a minus f of L, f of x plus L x minus a. So the difference between f and its approximating line. Then we can solve this and say that f of x is equal to f of a plus L x minus a plus u of x. And then we can calculate that u of x over x minus a is equal to the difference quotient minus L. And when we take the limit of both sides as x approaches a, this gives us 0. And so we get that we get therefore that f is differentiable at a with f prime of a equal to L. Let's now talk about the derivative of the inverse of a function. Suppose that I is an open interval and that f from I to R is continuous, a strictly monotone function. Say that j is equal to f of I and that g from j to R is the inverse of f. If x naught is in I and f prime exists and is non-zero, then g is differentiable at f of x naught and g prime of f of x naught is equal to 1 over f of x naught. Okay, so we're going to start here. We're going to, f is strictly monotone. We're going to assume it's increasing. As f is strictly increasing, it's 1 to 1. So g, the inverse of f, exists. Okay, we will show that g is differentiable at f of x naught. Okay, let y naught be equal to f of x naught, and suppose that the sequence yn is a sequence in J such that yn does not equal to y naught for any natural number n, and that the sequence yn converges to y naught. Let xn be equal to g of yn, and note that xn converges to y naught because g of yn converges to g of y naught, as g is a continuous function. Okay, and that g of y naught is equal to x naught. Okay, now let's do some manipulation of the sequences. Take g of x of yn minus g of y naught over yn minus y naught. That's equal to xn minus x naught over f of xn minus f of x naught, just by our notation. Now we can take that right hand side, make it the left hand side down here, and then it's equal to the reciprocal of our difference quotient, so that we take the limit as n goes to infinity of our sequence g of yn over g minus g of y naught over yn minus y naught. It'll be the limit of this other, which will give me, therefore, that g prime of y naught is equal to 1 over to f prime of x naught, which is to say that g prime of f of x naught is equal to 1 over f prime of x naught. We're now in a position where we can talk about our old friend, the chain rule. So let's let f be a function from the open interval ab to r that is differentiable at some point x naught element of ab. Let y naught be equal to f of x naught, and suppose that CD is an open interval that contains y naught. Okay, suppose that G is a function from CD to R that is differentiable at the point y naught. Then G composition F from AB to R is differentiable at x naught, and G composition F prime of x naught is equal to G prime of f of x naught times f prime of x naught. Okay, the chain rule. Okay, so the setup. Since f is differentiable at x naught, f is equal to f of x naught plus f prime of x naught times x minus x naught plus u sub f of x, where the limit as x approaches x naught of u sub f of x over x minus x naught is equal to 0. And similarly, we have this similar formula for g. Okay, with the u of g being our error function and it having the same goodness factor, that the limit as x, that y approaches y naught of g of u sub g of y over y minus y naught is equal to 0. All right, now consider that g composition f of x is equal to g of f of x, which is equal to g of y naught plus g prime of y naught times f of x minus y naught plus u sub g of f of x. Note that f of x minus y naught is equal to f minus f of x minus f of x naught, which is equal to f prime of x times x minus x naught plus u sub f of x naught. Okay. Therefore, okay, our g of f of x is equal to g of y naught plus g prime of y naught times square brackets of f prime of x naught times x minus x naught plus u sub f of x, close square brackets, plus u sub g of f of x. Okay, left off a parenthesis there, sorry. We can do some distribution and rearrangement of this to get g of y naught plus g prime of y naught f prime of x naught x minus x naught plus, okay, g prime of y naught u of f of x plus u sub g of f of x. So let us now set my u of x equal to the last two terms of this expression, and then calculate u of x over x minus x naught. Okay, we get this expression here. Okay, I can then do some rearrangement on it. Okay, that look at this u sub f of x over x minus x naught term. Okay. Do some clever rewriting in it. Put in a f of x minus f of x naught on the top, leaving off that parenthesis in the numerator and in the denominator. And now taking the limit as x approaches x naught, and we see that this goes to 0, and the other term, the u sub g of f of x naught, that will go to 0 as well. Therefore, I've got my derivative set up, and everything goes just as it should. Okay.